So recall snake lemma. So you have two exact sequences like this, A, B, C and D, E, F. These are given in green, and you have maps alpha, beta and gamma. So notice that the direction of the maps is kind of non-standard. So this, but then if you have a diagram like this will give you this sequence: kernel of alpha to kernel of beta to kernel of gamma to co-kernel of alpha to co-kernel of beta to co-kernel of gamma. So we are writing this in this form precisely because we want to use co-homology version of spectral sequence. So I have taken this entire lecture from the notes of Ravi Vakil's online notes on algebraic geometry. So this is, I think, chapter 2 on category theory. You can find it. So you see the spectral sequence introduction there. So he uses the same example. So I've taken it from his notes. So let us go on to now cohomology spectral sequence and see how easy it is to prove the snake lemma. So we have already done the snake lemma before in the playlist on snake lemma, but now see how easily we can do it using spectral sequences. Now we use the cohomological version of spectral sequences to prove the snake lemma. So in the cohomological version, the arrows are in the opposite direction to homology. So on page R, we move R right and R minus 1 down. So this is what we are going to use. So before we move on to the pages, first focus on the horizontal filtration of the total complex. So just view this as a total complex and just view the horizontal arrows. So notice the direction of the arrow. So we are taking cohomology instead of homology, so the arrows are going like this in our total complex. So you're just considering the horizontal filtration, and the premise of the snake lemma is that this is exact and this is exact. So in the total complex, everywhere else you have 0. These are the only two non-zero rows. So this is exact and this is exact, and since you have exact rows, that means the cohomology of the total complex is 0. So cohomology of the total complex is 0, and this is the infinity page of our spectral sequence. So infinity page computes the total cohomology, and we already know from our study of total complexes that if the rows are exact, you will get 0 as the cohomology. So we proved that in the homology case, and we carry over the same reasoning to cohomology case by simply reversing the arrows. So we now know that the infinity page just consists of 0 modules. So there are no non-zero modules on the infinity page, and this is important, which we are going to use. So first we work on page 0. So on page 0, so arrows go 0 right and minus 1 down. So R right and R minus 1 down. So you have 0 right and minus 1 down. So minus 1 down means 1 up. So the only non-zero modules are A, B, C and D, E, F. So everywhere else on page 0 you have just zeros. So these maps are already given to us as alpha, beta and gamma. So now we want to compute the cohomology at each and every non-zero module. So you know that 0 is going in here and 0 is coming out here. Similarly, 0 is coming out of here and 0 is going in here, because on the page everywhere else you just have 0 modules. So what is the cohomology here at A? So cohomology of here is just kernel of alpha, because you modulo out by image of something coming in, which is just 0. So what is the cohomology here? The cohomology here is co-kernel of alpha, because the kernel of this map is D, and from D you modulo out the image of a map coming in, which is image of alpha. So you get co-kernel of alpha. So cohomology here is co-kernel of alpha. The cohomology here is kernel of alpha. Similarly here, so the cohomology here is kernel of the arrow going out over image of the arrow coming in, but kernel of the arrow going out is kernel of beta. Image coming in is just 0, so you have kernel of beta. Similarly here, the cohomology here is kernel of the arrow going out, which is entire E, modulo out image of arrow coming in, which is image of beta. So this is co-kernel of beta. So similarly you have cohomology group here is co-kernel of gamma, and cohomology group here is kernel of gamma. This 0 0 will give you 0 0 here, you have 0 0 here, 0 0 here. So on page 1, these are the only non-zero items we see here: co-kernel alpha, co-kernel beta, co-kernel gamma, and kernel alpha, kernel beta, kernel gamma. Everywhere else is zeros are just sitting. So what are the arrows? So on page 1, you will move 1 right and 0 down. So page 1, you have 1 right and 0 down, just using this formula right here. So you just go 1 right, so all the arrows are going like this. So all the arrows are going like this on page 1. So now we come to page 2. So for page 2, first you compute the cohomology at each point. So cohomology here you denote by this double star. Cohomology here is this single star. Cohomology here is this 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 double star. So now we are working in page 2. So for page 2, you again use this formula. So you have 2 right and 2 minus 1, 1 down. And that's what you see. So this 0, you go 2 right. So 1 and 2. So 2 right and 1 down. So again here you go 2 right, 1 down. Similarly from here you have to go to 2 right. So and 1 down. So on. So 2 right and 1 down is what the arrows are. Now notice that the infinity page is just consisting of 0 modules. So notice at this star. Now this star, 0 is coming into the star and 0 is going out of the star. So on page 3, this star would not change. So whatever cohomology we have computed here will remain the same on page 3, because 0 is coming into it and 0 is going out of it. So the kernel of the map is just this entire star which we have computed from here. We do not know what we have computed. We are saying we have computed something, but it is not going to change on page 3. So since it is not going to change on page 3, it will not change on page 4 and so on. So it will not change till page E infinity. But on E infinity you have this as 0. So this is 0. So this is therefore 0, because this stabilizes right here. Similarly for this star, if you take an arrow out of it, it will go to 0, because these stars are the only non-zero components in the entire complex. So arrow coming into it and arrow going out of it is also going to 0. So this is also stabilized. So since this is stabilized, so this will remain same on page 3, same on page 4 and so on. So it will be the same on page E infinity, but we know on E infinity everything is 0. So this is also 0. Similarly here you can see on page 3 the kernel of this map will be the cohomology, but kernel of this map is just this star, and after page 3 it will be stabilized just like it is stabilized here. So it will remain star till page E infinity, but on E infinity this is 0. So this is also 0. Similarly this is 0. Now these are zeros, that is fine. You have a problem right here, because this double star in green is getting mapped to double red star. So you do not know what is in the kernel of this map. You just see these two things. Here we knew that this entire module is getting mapped to 0. So here we do not know. But let us just focus on what we already know. So we know the cohomology here is 0, cohomology here is 0. So this corresponds to this portion here. So you have exactness here. This is cohomology is 0, so you have exactness here. This is 0, so you have exactness here. This is 0, so you have exactness here. So now the only thing you want is you want to construct a map from here to here. So say this map is delta. So this is the map you want to construct. So for this, notice that when we go to page 3, so the next page we go to page 3. On page 3, we will put down here the corresponding cohomology here. So that is the kernel of this map. So on page 3, we will put the kernel of this map in the corresponding square. But the arrows in page 3 are really long. So the arrows will be longer than this. So the arrow will overshoot this, because the arrow on page 3 will go 3 right and 2 down. and if it goes 3 right and 2 down, then it will only hit zeros, because these were the only non-zero components. So these were the only components which were going to give you non-zero cohomology. So these arrows are going to overextend. So whatever we compute here, the corresponding cohomology, which is just the kernel of this map, will stabilize. So the corresponding this cohomology is just kernel of this map. Now we know on the infinity page everything is 0. So we have to have the corresponding cohomologies which we compute from here to be 0 rather than some values on page 3. So only way to achieve that is if you have an ISO here. So if you have an ISO here, then you do not have to worry about the next page, because on next page you will just get 0. So we just talked about how on the next page you will have special cohomology groups, but we want them to be 0 because they will be stabilized after page 3. So you want this to be an ISO, so you just get zeros on next page. So for this to be an ISO, this double star, which is the corresponding cohomology for this map here. So the cohomology for this map is just kernel of co-kernel alpha to co-kernel of beta. And this double red star corresponds to cohomology computed right here. So the cohomology computed right here is co-kernel. So co-kernel of this map, kernel of beta to kernel of gamma. So because this is lying at the end of the sequence, since this lies at the end of the sequence, the only way to compute cohomology is to take co-kernel. Just like 0 is coming out, so you always take co-kernel. So similarly here 0 is coming out, so you take co-kernel. And so here you're taking co-kernel of alpha. So instead of co-kernel of alpha, you can write co-kernel of the map from A to D. So similarly here we are writing co-kernel of the map from kernel of beta to kernel of gamma. Nothing much. Exactly the way we have done this, we are writing this. Only thing is advantage, we have defined alpha here. Here we are just writing the map. Similarly here. So you have this equality. So if you have this equality, then you can glue these pieces together. So why you can do this? This I have already explained in the lecture on exact sequences. So this lecture is the first lecture in the playlist on snake lemma. So the first lecture I explained how to cut and paste two exact sequences or long exact sequence. So therefore now you have the co-kernel of this map is equal to kernel of this map. So co-kernel of this map is equal to kernel of this map. Therefore you can glue them together to get the snake lemma. So this was an easy application of spectral sequences, and it helped us understand how to use them. So this is the most used application. So the first thing you always notice is if there is a horizontal filtration or a vertical filtration, with either you have exact rows or exact columns. So if once you have exact rows or exact columns, that immediately gives you that page E infinity just consists of zeros, and then you play things with each other to get something which we do not know. So we did not know about alpha, beta and gamma, so and this was exact, so we did not know something about this, and the spectral sequences gave us a relationship like this.